Okay, so welcome to the session on the digital signatures 3. The first paper will be presented online. It's on digital signatures with outsourced hashing by Simon Rastikian and Bertram Pöttering. And
Okay, thank you very much for the introduction. I'm sorry I couldn't make it to Asiacrypt in person. But I give this presentation now anyway to give you an idea about what our paper is doing. What I'm presenting here is on outsourced hashing and signature schemes, and everything I say here is joint work with Simon Rastikian, who got his PhD just 2 weeks ago. So this is why I like to stress that he's a doctor now. Let me tell you first about signature schemes. This is, of course, all of you know what a signature scheme is, but this is the notation I'm going to use. There's a sign algorithm, a verification algorithms, and I will never write down key generation algorithms. Sigmas are signatures, SK, VK, 0, 1, that's all clear from the context. So that is the way we abstract signature schemes from the provable security perspective. Technically, however, signature schemes have a little more structure that one could point out. And a very classic way to compose signature schemes is with the so-called hashed and signed paradigm. I personally do not like this term too much, but I use it here because it's underdefined. But roughly what it wants to say is that a signature scheme, so this blue block here, the outer one is still the signing block that we had before, but internally, the message is put into a hash function, and this uppercase H here stands for SHA-2 or SHA-1 or SHA-3, whatever you like. And then only the hash value goes into a signing core, and that's where the number theory sits. That's where your RSA is, or your elliptic curves, or your lattices, or your code-based system, or whatever. So this is a way to construct signature schemes, but that's only one of the major two classes. Another class is a little bit more involved, and we call this the interactive hashed and sign case. So the one on the left that I just talked about was the strict hashed and sign, because we have hash first and then we go into the core. But Schnorr, as an example, Schnorr signatures and everything that comes out of the Virchow transform has actually a little bit more complication in the hashing, because I need to plug in Schnorr signatures also G to the R, where R is the ephemeral randomness, into the hash function. So basically, I need H to be a random oracle. H will still be SHA-2 or SHA-3 or something, but I have R, M. And that means the signing core, there's here this added arrow up that we didn't have on the left-hand side. So the signing core will contribute some value that to the hashing, then goes the message into the hashing, and then this goes back to the signing core. So this is two major class, and I guess effectively this will cover 95% of all signatures that we have out there. So again, H of M, that's the strict case, H of something, M, maybe then again some technical information, that would be the interactive case. Now, these structures, they don't appear in the generic versions that we kind of, as in the domain of provable security, like to think of signature schemes. But in practice, these structures are exploited, namely the separation of hashing and the core of signing or the core of verification. That is what practitioners actually love to use, and they do this regularly. And I gave you an example, or some examples of this. The one is in trusted hardware settings. For example, the core of this signing could be implemented in a smart card, and the hashing could be in a host PC to which you connect the smart card. For example, if you sign a document, a PDF document, 100 megabytes document with Adobe Acrobat, then the PDF viewer software will compute the hash value and send only the hash value to the smart card. And then the smart card is going to complete the signature sigma out of this. So this makes these construction paradigms, so the way the signature schemes are constructed under the hood, very interesting from a practical perspective. We call this, so the title of this presentation was Signatures with Outsourced Hashing, and this is from this perspective that the smart card, or whatever the trusted hardware is, can outsource the hashing operations to another entity that is possibly better in computing, working with large documents, or is just where the data is, because the document is in the PDF viewer and not in the smart card. Another motivation would be a software stack. So you want the signing core, for example, in a low-level system library, which is optimized in assembly language and really understands how side channel, what the side channel conditions are in a PC, while the hashing you want to do where the data is, and that means then an high-level language like Python or PHP or whatever your application is. And for this separation between the hashing and the core, there is even industry standards. PKCS 11 will regulate this for which is optimized, which looks in particular in smart card setting, but also TPMs and so on. And they have in this standard, which was written in the 90s and early 2000s, they will tell you how to exactly implement ECDSA or DSA or RSA with this separation, where one entity will hash and the other one will compute the signatures. Now, this raises two questions, namely, first, hashed and sign. In this case, it's clear what happens. The hashing would be done in the PDF viewer, for example, and the core in the smart card. But in the Schnorr case, it becomes less clear because you have this interaction, and so the interface is a bit more unclear. So how can we do this in this case? But much more importantly, from my perspective, is this actually secure? We have security proofs for signatures, but then in practice, one uses them differently and distributes tasks amongst different entities. And the trust model is very important here because you have a smart card precisely because you do not trust your host PC. So what happens if you trusted suddenly the host PC to hash your message properly? So this is important questions in this topic, which were partially explored already in another publication this year, to which I come after the second slide. So I would like to refine the syntax a little bit more that will be relevant in this talk. What you see here on the lower part is the conceptual explanation of what hashed and signed signatures look like. But the way we formalize this is this one, which is similar, but not exactly the same. Namely, we split the signing core into two algorithms, signing initialization and finalization. They are stateful, but there's only one invocation of this, then a stateful invocation of the second. Together, they need to create a signature, and the hashing is separate. The initialization will provide a hash seed, and the hash function will output a hash value. And the hash algorithm, of course, will consume also the message. The dashed line here in the middle suggests the physical separation of the two entities of the hashing and of these cooperations. Let me now switch to the prior results. That is by the same authors as the current paper, and this was presented at PKC this year. This paper, so the PKC paper, looked only at the strict separation. So the separation in the strict case, that is first hashing and then the core, and not the interactive setting. And the negative results of that paper were that there is signature schemes that become insecure if you separate the hashing from the signing. Examples for such insecure schemes would be RSA and BLS signatures. That is because if I go back here, there is too much homomorphism properties here on the hash value side here. So if the hash function is not trusted, then it can kind of blind the hash value it calculates, get a signature on this blinded value, and then the adversary could unblind this. In a nutshell, this is how these attacks would work. But there's also positive results, namely the DLP-based signatures that you all know best from standards. In particular, ECDSA, they actually remain secure. So this ECK CDSA is the Korean version of ECDSA, SM2 is the Chinese, and GOST is a Russian signature scheme. They are somehow all different and all the same at the same time. And the reason why they stay secure is because they actually run these two hash functions, or this conversion function, which would play the role as the random oracle in this case. But this paper from PKC also gave a very general, constructive, positive result, and that is it explained how Merkle-Damgard hashing stays secure in all cases. So, sorry, signatures that use a hash function that is a Merkle-Damgard hash function can stay secure in general, and I explain this detail too here because we are extending on it in the current paper. Let me remind you of how Merkle-Darmstadt hashing works. So we have a compression function here in light blue. We have an initialization vector on the left, and then there's this chaining operation to compute the hash value, and the message is cut into blocks and goes into subsequently into all these compression functions, and the last block might be partial and has to be padded. So that's how Merkle-Darmstadt hashing works. If I want to use this in a strict hash and sign setting, I need to map the upper part into this pink block here of the hash and sign signatures abstraction. And the question is how to do this. And the immediate way to do this is this one, that basically just the whole Merkle-Darmstadt chain goes into this pink block. So this is the natural way. I call it the naive way, but it is the one that is actually insecure. So the negative results from PKC show that this in general is not a good idea, but the good idea that we identify in that paper is that one should actually shave off the last compression function call and put that into the finalization routine. So everything that is now pink here, that is all but the last block, would go into the hash block here, but the last compression function would go into the finalization, and then we can, if we model this compression as a random oracle, the compression function as a random oracle, which is a acceptable assumption for SHA-2, for instance, then this becomes generically secure. Now, that is from PKC, and now let me switch to the current paper that we now have at Asiacrypt. We look this time not at the strict case, but in the more involved interactive hashed and signed setting. So recall that is where the signing core first puts information into the hash function and then the message is added. Again, we have negative and positive results. The negative results, and they read the same basically. The negative results are that some DLP-based signature schemes are totally insecure, and the positive results are that some DLP-based signature instances are provably secure. So remain their security under the same conditions basically as the signature schemes without any separation would have had. And the key insight here, which makes this very interesting from my perspective, is that whether a scheme is secure or insecure depends very crucially on the characteristics of the hash function. So SHA-2 is different, or SHA-256 is different than SHA-384 as we are going to see. And also the specific properties and representation sizes of the elliptic curve matter here. So do you have a 256-bit curves or a 384-bit curve? We also, on the positive side, show that how to operate signature schemes based on Merkle-Darmstadt hashing is secure in general, or how to operate them in a secure way. So let's go into the details of the letter. So again, this is the reminder of how Merkle-Darmstadt works. There's no signature components here. In the case of Schnorr signatures, as an example, we now need to switch. So I go back one slide here. So the Merkle-Darmstadt would just compute H of M. But what we need to do now in the Schnorr case is compute H of R concat M. And that, of course, works by first hashing these group element R, and then feeding the blocks of M into the compression function. So that's the picture. And now I need to map this to this case. So again, I need to identify what will be the green part and what will be the pink part. And then the natural way to do that is like this. So the signing operation will produce the ephemeral randomness of the Schnorr case and compute these compression function calls here in the beginning inside the core. And then the hash state at that point, the Merkle-Darmstadt chaining value, basically, that would be forwarded to the pink block here. And eventually the pink block would come back to the finalization algorithm, again, communicate only this chaining value. And then the finalization would first complete the finalization of the hash function and then compute the signature on that. Now, that is how we would split it algorithmically. But the question is, again, is this secure, and what are the problems and what are the challenges connected with this? And the problem is they are twofold. The first one is concurrency, and the other one is extra information leakage. Let me go back. The concurrency comes from the statefulness here. So if I want a signature from my smart card, the smart card initializes, creates a state, and waits for a hash value coming in. But no, let's not talk about smart cards. Let's talk about TPMs, because TPMs will support concurrent signing. That means while the instance is waiting, I could want a second message signed. So I run this signing a second time, it creates a second state, and then I can actually have concurrent signing operations. This was not a case ever before with signature schemes, and well, there's interactive ones and blind signatures, but I mean, with standard EUF-based signatures like ECDSI, this concurrency was never an issue. And the second issue is the information leakage, because now I need to commit and possibly leak on some partial information of my randomness R, the ephemeral randomness, the group element, before the adversary would have to commit to the message that is going to be signed. And both of these are problems, and they lead to severe problems, forgeability problems. Namely, for Schnorr signatures, we can demonstrate universal forgeability if this R value can be recovered from the hash state. So going back here, so if this group element R can be recovered. Hello? Okay, I had some audio input here. I don't know what this is. So the R value can now, if the R value can be recovered from the hash state, then we can demonstrate universal forgeries, meaning we can forge on arbitrary messages, exploiting this concurrency and this information leakage. On the other hand, if the R value is aligned with the block boundaries of the hash function, so meaning that this concatenation is actually a trivial one in the sense of that first all the R's are consumed and then they compressed into one single chaining value here, then actually we can use forking lemma-based proofs as before and reestablish security. Now, what does this mean in practice? So I said already there is this alignment property that we need. And now we come to the practical cases. Whether these values are aligned or not depends very much on the hash function in use and on the representation size of group elements. And we created for a couple of real-world DLP-based signature schemes, graphs, figures like this. So this is for Schnorr DSA, which is, yes, it's outdated, but I'll give you more schemes on the next slides. So this is a Schnorr DSA standard by the German BSI. So that's basically Schnorr signatures, standardized. And I have on the y-axis here different hash functions, SHA-1, different versions of SHA-2 and SHA-3. And I have here different finite field sizes. So this is really finite field DLP, and this starts at 1024 bits and goes up to 4000 bits. And the green in the upper part, you see green symbols, and this means these versions are secure. For the red bullets here, so we have 6 red bullets in the bottom left. This is the cases where we can demonstrate universal forgeries, and the yellow parts are a bit unclear. So this is where we cannot exclude that forgeries exist, but we also cannot confirm them. This is finite field stuff that is outdated. On the next slide here, we look into 4 different versions of Schnorr signatures as they are standardized on elliptic curves. Now I replaced on the x-axis the finite fields with the elliptic curve bit sizes, starting at 160, going up to 512. And we see again that some versions, for example, let me pick out this one, which is ECSDSA. This is again by the German BSI. Some versions are provably secure. This is the one with the green symbols here in the upper right. And most versions are actually insecure. In particular, as a common pattern here, everything, both on this one and on this one, everything that is about SHA-3 is insecure. Oh, we do not have provable security in these cases, and this has to do with the extremely large block lengths of SHA-3. So recall that's 1,600 bits is kind of the input to the permutation, and that means that the whole group element is swallowed. It's not even processed once through the permutation in this case. And this brings me to my last slide, namely the conclusions, brief conclusions of what you could find in the paper. If you're interested in reading it, first we continue the study of these hashed and sign signatures from a practical perspective. So really from the first time from this industrial perspective of taking advantage of separating the hashing from the signing core. Prior work looked at strict HDS. This work looks in the interactive case, which is more involved, but also has more interesting results with this universal forgeries versus the provable security proved for the very same scheme, just different settings. We formalized the syntax and total at least 4 security models of this, depending on different trust models that we can assume on the adversary. Can the hashing be trusted at all, kind of that it's only leaking information, but is honestly executed and so on. So you will find different trust models here. We give a detailed case study for DLP-based signatures. And the very key finding here is the one connected to these colorful figures is the group representation size matters and the hash function block size matters most. And future work could focus on A. What is the best advice for standards on signature schemes? It looks like it is always a good idea if one uses PHME transform to pad the technical information, in Schnorr case, the group element or whatever your commitment is of the underlying Sigma protocol, to pad that to a full block size that is sufficient for Merkle-Damgard hashing as we proved, but it is not necessarily sufficient for sponge-based hash function. That is because sponge-based hash functions, the permutation is invertible. So even after running one iteration of the permutation, you could undo this. So you need at least one more iteration of the hash function. So it's not clear exactly how to do this in the SHA-3 case. Then some practical signature schemes like EDDSA will actually hash the message twice. That is because they want to be deterministic and not randomized, and so they need to compute the ephemeral randomness with a PRF from the very message. That means they first run it to get the randomness. They first run over the message to get the randomness, and then they run a second time to compute actually the signature. So this is not covered by our syntax. This requires a change of syntax and also new security models. And the last open thing would be separating more the yellow from the orange cases. So let me go back here. Orange means, yellow means we don't have results, and orange means we are almost there, but our attacks are not complete. So we don't consider it likely that there is attacks in the orange cases. And with this, I conclude my talk. Thank you.
Okay, so does anybody have a quick question?
Are there any similar work on PQC?
No, that's also ongoing. I just forgot it in the future work part. The PQC signatures are similar and different. So they are two different from the ones we looked at that we would make general statements, but we believe that is pressing work that needs to be done to analyze those two, because they are the relevant ones. The DLP-based ones are well understood from both implementational perspective and from security analysis, but they do not represent the future. So I agree that makes a lot of sense to look into this, but we do not have results at this point.
Thank you.
Okay, then we're also over time. So let's wrap this up and continue with the next speaker. Thank you for the talk.
Yeah, thank you.
So the next talk will be on non-interactive blind signatures, post-quantum, and stronger security. The paper is by Fonteni, Baldinti, Diaki Cheng, Rishabh Goyal and Ayush Yadav, and Ayush will give the talk.
You hear me? Okay, so how about this? Is that better? Okay. So thank you for the introduction. This is joint work with Pateni Balbinsi, Jackie Cheng, and Richard Boyle, and is on non-interactive blind signature. So let's start quickly by recalling what a blind signature is. A blind signature is a protocol between a user and a signer, where the user wants the signer's signature on some message meaning, but does not want to reveal the message meaning to the signer. To do so, the user first creates a blinded value beta, sends over this blinded value to the signer. The signer then takes this blinded value and creates what I will call a pre-signature or a blind signature, and sends this pre-signature back to the user. The user can then extract from this pre-signature, can extract a final signature that verifies on the signer verification. Just noting that this is the way I've shown this here is an example of a round optimal protocol. So there's only one round of communication between the user and the signer. In general, this need not be the case. A blind signature must satisfy two security properties. First, it must be unforgeable, in the sense that the user can only obtain valid signatures on messages by interacting with the signer. Typically, this is modeled as a one more unforgeability experiment, where the adversary makes k queries to a signing oracle and then outputs k plus 1 forgery. Also, the blind signature must be blind, or must satisfy blindness, in the sense that the signer should not be able to link the the message and signature pairs to any specific signing type. Since its introduction over 40 years ago, blind signatures have found many applications in, for example, in cryptographic tumblers, anonymous credential schemes, anonymous web browsing, and however, a major limitation of these interactive schemes is that it requires both parties to be online for the signature issuing. So the question is, can this protocol be made non-interactive? And intuitively, the answer seems to be no, right? I mean, you do need at least two movements. You need one blinded message from the user to the signer, and you need a pre-signature or a blind signature from the signer back to the user. And indeed, that is true. With the caveat that it's true when the message is specified by the user. In a very recent paper, Hanslik noticed or observed that that in many practical applications, this message is often chosen randomly and has no specific type. And in that case, there is a non-interactive signing procedure. This gives non-interactive blind signatures randomly. And at a high level, the protocol proceeds as follows. So first, now the user must create its own public and secret key pair, and then the signer also has that. So there's some sort of PKI where you have all these public keys. But this is done once as well. Then to issue a pre-signature to a user, the signer does the following. The signer samples some randomness. It then issues a pre-signature using the user's public key as well as the randomness, and then sends both the pre-signature as well as the randomness. Then the user can extract from this pre-signature. It can extract both the message and the signature using its secret key. And then this, of course, this message and signature will verify on the signer side. So this NIBS protocol, the non-interactive blind signatures, this NIBS protocol should also satisfy the same two security properties. It must be one more enforceable in the same sense, and it must be blind. Unforgeability is defined similarly or can be extended similarly from the interactive case, but blindness requires a little bit more. And so let's look at how the previous work defines them. So the game is between a challenger and a malicious signer or the adversary. The game begins with the challenger sending to this signer, to the adversary, two public keys. These can be the same public key, or these can be distinct public keys. The signer sends back a verification key and two pre-signatures, also demanding, but just assume that it's included. And then the user will extract the messaging signatures from these two pre-signatures. Here I've colored them red and green. So just for simplicity, I'll call them the red and green tokens. It takes these tokens and then it sends them over back to the admin. Before it does that, it's basically going to rearrange them based on a bit that it's sampled by. So it shuffles these tokens and then sends them over. The security requirement is that the signer should not be able, or the adversary should not be able to tell which of these tokens is red and which of these is green. And yes, this does seem to capture the notion, some notion of it. But it turns out it's not quite the notion that we want. In fact, there exist switch protocols that are provably secure under this line of definition, but are easily broken under very minor. So let's see what breaks down. The problem is that this definition restricts the case where the adversary receives exactly two messaging signature pairs from the challenger, which in general need not be the case because a signer could see many messaging signatures. So consider this very simple example where we have a red user and a green user. And an honest but curious signer issues two pre-signatures to these users, to the first user, and then one pre-signature to the second user. Then later, let's say the first user comes back and shows when the same user comes to the signer with two tokens, the signer can be almost certain that they must be from the first user, the red user. And moreover, when the second user comes with one token, not only does the signer learn that it's from the second user, it also learns that it's linked to this specific pre-signature. So clearly this is a problem. And in this work, we begin by sort of fixing these. And the way we do that is by providing the adversary with access to an oracle, an obtain oracle, where the adversary can now make pre-signature plays and get back as many messaging signatures. And so now, like I said, well, now the security should hold for an unbounded number of functions. So pictorially, the adversary now has access to this signing oracle, obtain oracle, to which it can make pre-signature plays and get back final messaging. You can kind of think of this as like being the encryption oracle in the CCA. And our claim in this work is that the stronger definition of blindness is the correct definition that captures the actual baseline requirements for eternity. All right, so with the definitions now fixed, we take a step back and look at what previous work, what kind of construction for previous work. So they give a generic compiler from Needy proofs and VRF, and they give pairing-based construction, which is secure in the idealized model. And as a side note, we believe that both these constructions do satisfy the stronger definition of blindness that we just did, although there's not a strict. However, the first construction is somewhat complicated using rather heavy objects and leads to large signals. Secondly, there's no post-quantum security in the time. So now our goal for the rest of the talk will be to sort of remedy these two issues, to address these issues. And to do that, we turn to Fishman's paradigm, which is a well-known generic construction for interactive ranking. And you can ignore the notation here. I'm going to abstract this out. So in the scheme, the user wants to get a signature on a message new. To do that, the user first creates a commitment to its message. If this commitment is hiding, then this is essentially the blindness operation. It sends over beta, and the signer will sign this data and send over the resulting preset. Then the user simply creates proof of knowledge that it knows a verifying signature on data corresponding to the original, on commitment data corresponding to the original. And so now the signature is just pi for the message new. And a verifier can simply verify this proof. So now, given this, we asked, well, how can we adapt this to the non-static? What we realized is, well, the public key, the user's public key in the non-interactive setting should somehow act as this commitment data. And in order to do that, however, the issue is that we only have one public key, but somehow we want the user to be able to extract an unbounded number. So in other words, we want that the public key should act as a succinct commitment to an exponential number of messages. So that's the first one. And the second challenge is that the signer must sign the commitment in a way that the signature, well, what I mean is we want that unforgeability demands that the signature should bind to exactly one message. And that means well, that should bind. Anyway, so said differently, the challenges are how to commit to an exponential number of messages returning, and how to have the signer obliviously select exactly only one of those messages. So the solution is quite straightforward. We use a PRF. The user's public key is a commitment to some PRF feature. And the signer simply samples a randomness R and signs both PKU and R. The final method is just the PRF evaluation of R, and the signature is a proof of knowledge of the pre-signature on PKU and R, corresponding to the original. So again, to illustrate this, the way it works is the user first creates a commitment to the PRF key, and then the signer will sign both PKU and R. It will send over the pre-signature and the randomness, and step mu is the PRF evaluation of R, and zero knowledge proof for knowledge of the commitment. The proof is, well, the signature is just, as you would expect, and for both the security proofs are quite straightforward. And unforgeability follows from the argument of knowledge property of blindness and unforgeability of the signature. For blindness, for strong blindness, we require the zero knowledge property as well as hiding the code. So quite straightforward, so I'm not going to discuss the proof. However, I do want to point out that while this pre-signature is optimal in size because it's just a plain signature, the final signature is quite large because it's a zero knowledge. In practice, we would rather want the opposite. We would want to have a small final signature, and we might be willing to pay with a larger pre-signature. So that's what we do next. We ask, well, instead of using this NIS to hide the user's secrets, can we instead make the server do some homomorphic computation to directly compute the signature on the signer? And indeed, that is possible. The way we do this is, first, we now set the user's public key to be the encryption of a PRF feature. And then the signer simply homomorphically evaluates a signature on the message SK of R for some R that is changed. The final signature is just the PRF evaluation of R. And the signature is an actual signature, which, well, the user can decrypt using the secret. So again, pictorially, the way it works is the public key is encryption of PK, and the user will evaluate the ciphertext on the circuit C, which is just a signature on the PRF evaluation on R. And it will then send over both the pre-signature as well as the randomness. And like I said, the message is the PRF evaluation and the signature. So the security proof is again quite straightforward, so I'll just skip it, but I will mention that you do require a slightly mild assumption that it's homomorphic encryption should be circuit-type. And well, this construction can be instantiated from standard lattice assumption. And this gives the first theoretical construction for post-quantum security. Right? This table also summarizes the contributions. This is the construction that I just discussed. It has optimal size because the final signature is just an actual plain signal. This is the construction that I discussed before that. And we also give a lattice-based construction that has quite optimal, quite efficient parameters, but it uses a non-standard lattice assumption that we also give. This assumption is required to prove composability of this group. And however, the caveat for this is that it's only secure under the weaker one-time blindness given in previous work. To summarize our results, we identify an issue with existing definitions and give the right definition for mid-blend. We also give a new correctness notion, which I didn't talk about. We give a Fishman-like compiler to NID and prove security in this baseline setting. We give a generic construction for NID from homomorphic encryption and prove security in our new baseline setting. We also give a construction from a non-standard lattice function, which we also give in this work, called the randomized normalized function, and is derived from a previous work of Abelard et al. It satisfies the weaker one-time blindness notion given in previous work. Finally, in terms of open problems and possible future work, we have the following interesting problems that we came up with. The first being coming up with an efficient post-quantum security that satisfies the baseline blindness test. Then we would also be interested in a formal cryptanalysis of the randomized one-more assumption, which I did skip over, but I encourage you to read it for detail. Then again, we also don't have mid-from pre-assumptions, which could be an interesting area for more efficient, more concretely efficient. And then again, we might be interested in other models for non-transfer science. I do want to remark before I put in that we do have an upcoming work where we solve the first problem of somewhat efficient post-quantum for some lattice assumptions using combination of standard and non-standard. And thank you for your attention. That's the verification.
Yeah, thank you for the talk. So, does anybody have any questions?
Thanks, great talk. Did you implement any of the instantiations?
No, so not really. Like a lot of those would be quite impractical to implement, but we did do some parameter estimates for the last one.
Okay.
I mean, that is another interesting thing that we're.
Okay. Thank you.
So what do you mean by strong blindness? Like, do you mean to say, what do you call malicious settings you are talking
so
about, or honest setting?
Yeah, so by strong blindness, I just mean the blindness definition that we give in this book, right? which gives access to this oracle for pre-sale, this obtain oracle. So kind of the issue with the previous work was that their blinding definitions were weak and incomplete. So by strong, I mean the new baseline definition for blindness.
So here, the secret key is generated by the challenger.
No,
Not really. I mean, the adversary itself.
the, well, who's?
Pardon?
Who's?
Signer point of view.
Yeah, we sign with the adversary again.
Okay, but isn't it?
And the adversary just
model, right?
output a verification. Adversary is happy.
What are your question about pairing-free instructions, nibs? Is your first compiler, I guess, would there be any barriers to instantiating that in a pairing-free way? And maybe it's just a question of how would you do an efficient pairing-free
I
construction?
would say, yeah.
Okay, so if there are no more questions, then let's thank the speaker again. And the next talk will be online again. It is on practical blind signatures in pairing-free groups by Michael Kloos, Michael Reichle, and Benedikt Wagner. And Michael Reichle will give the talk.
Yeah, thanks for the introduction. I hope audio-wise everything is okay. Okay, if there's no problems, then yeah. So yeah, thanks for the introduction. I am going to be talking about practical blind signatures in pairing-free groups. And yeah, as said, this is joint work with Michael Kloos and Benedikt Wagner. So we've seen blind signatures in the previous talk, so I'll just give a brief overview again. Essentially, yeah, we have a signer, we have a user. Both have access to a public key of the signer. The signer also knows the secret key that is associated to the public key. And the user has a message M and it wishes to obtain a signature for this message M. So in this case, we're in an interactive setting, so there's more than two messages. Later, our protocols will essentially have 2 round trips. So yeah, and essentially then in order for the user to obtain the signature on the message M, they will engage in a interactive protocol. And at the end of the protocol, yeah, the user obtains the signature sigma, and by correctness, this should verify correctly with respect to the public key and the message. For blindness, what we want is that the signatures are unlinkable to signing sessions. Essentially, this means that even if the user later on presents the signer or any other person the pair sigma and M, then the signer cannot even link this to the signing session. Yeah, even though it knows, yeah, even though it of course might have logs for the signing session. So yeah, this is blindness. And for unforgeability, what we generally want is one more unforgeability. So that means essentially the user can obtain at most Q signatures from Q sessions. And yeah, in this work, we're talking about signatures with distinct messages. And I mean, this can be strengthened to strong one more unforgeability, but yeah, in this work, we are interested in like baseline one more unforgeability. And this can be characterized even further, essentially into OMOF1 and OMOF2. For OMOF2, it's kind of the intuitive notion where we count all the finished sessions towards Q, because those are the sessions where the adversary kind of trivially gets a signature for. So for these sessions, it of course must provide 1 signature and then plus 1 forgery. Slightly weaker is the notion of OMOF1, where also the started sessions are counted towards Q. So this essentially means that even though the session wasn't finished, the adversary still asked to provide a signature for this. So this is a bit less intuitive why this makes sense, but it's still quite difficult actually to obtain for blind signatures. So it's still a notion that makes sense. It's just at least from like a theoretical point of view, a bit less weak, a bit less strong. So yeah, in this work, we're interested in blind signatures in the pairing-free setting from in the RAM Oracle model. So in order to kind of place our result in the literature and give you kind of an overview, I wanted to give a brief timeline of what happened in this setting. So I'm only concerned, or in this overview, I'll only talk about the pairing-free setting, and it's also just a selective overview. So I just want to give like a rough overview of the area. I don't want to, I'm not claiming that this is like a full overview, and I'm not including all the works. So yeah, sorry if but in particular yours was missed. This was not this is just because of time. So right, so initially the first scheme that were provably secure were from Poincheval and Stern. This is kind of like a Schnorr-like blind signature scheme that is provably secure in the sense that it has polylog one more unforgeability. So polylog means that at most polylog many concurrent sessions can be opened, and then the scheme remains one more unforgeable. This was then also generalized by Abe and Okamoto in the year 2000 to partial blindness, where the user and the signer can agree on a public message that both know that is also signed in conjunction with a private message. And this was then by Haug, Kills and Loss generalized in 2019 to other settings. And yeah, so this kind of, I would say, at least in my point of view, gives the foundations for this area. And in 2001, Abe gave, so of course, polylog unforgeability is a bit weak in practice and a bit unsatisfying. So the question is, can you do better than that? And Abe gave a positive response to this in 2001. So so at least from a construction point of view, this essentially solves the problem, and it has like a very it has a good intuition, and kind of the scheme is seemingly secure. The main problem is that there's a slight gap in the security proof in the random oracle model, so it's a bit unclear whether this actually is one more unforgeable. So in 2006, Fission essentially answered the question definitely by giving the first generic construction. So you can, of course, also unsensate this with pairing-free curves. The main downside of this is that this is a non-black box construction, and at least in pairing-free curves, this will be heavily inefficient. And then kind of in a very important work by Hamouda, Lepoint, Loss, O, and Rekova gave in 21 an attack on the Ross problem. So essentially Schnorr observed that underlying all of these Schnorr-like blind signatures is essentially this Ross problem. And if you can solve the Ross problem efficiently, then you can essentially also break these signatures. And essentially the Ross problem was in this work broken for roughly logarithmically many concurrent sessions. So this essentially shows that the proof of the schemes that are marked with the skull here is essentially tight. So this, of course, opens, and gives rise to the question, can you actually do better than that? So can you actually get provably secure and efficient schemes that don't have this polylog restriction? And this was answered in 22 by Kastner, Loss, and Xu, where they gave the first proof in the AGM for Abe's scheme. So it is provably secure in the AGM. And also Tesaro and Su gave in 22 a very elegant construction that essentially is as efficient as blind Schnorr. It just requires one more additional ZP element. The structure is a bit different, but it's still very efficient. So and this was then later on also optimized by Kreitz, Komomala, Tesaro, and Su in 23. So in short, in the AGM, we have actually very efficient constructions. And even outside of the AGM, so if you make, this is a work by Fuchsbauer and Wolf in 24. It's also heuristic, and it's a non-black box construction, but at least signature, so communication is not that great, but at least signature-wise, it's very short because it just outputs Schnorr signatures. And kind of, I highlighted a few things in red here on the slides, and this is essentially kind of one big open question in the field was, can you remove these caveats, and can you essentially prove in the pairing-free setting, can you build blind signatures that are actually secure in the random oracle model from standard assumptions? So no AGM, no non-black box constructions, etc. And this was answered by Champ, Tesaro, and Su in 24. So this is kind of a very recent work in terms of that essentially resolves this question, and they managed to build essentially exactly this, pairing-free blind signatures that don't rely on the AGM. And essentially our work essentially looks at their construction and their techniques, and we try to optimize efficiency. So in order to give you a bit more background, because we want to improve efficiency, I briefly recap roughly the efficiency that CTZ achieved. So they gave 3 constructions. 2 of them are roughly similar in terms of efficiency. There's just a difference in terms of a number of rounds and the security notion that is achieved. So these the first 2 constructions are very efficient in terms of communication and signature size. They essentially build on BLS, but they only achieve OM of 1, so the weaker notion, and they rely on a 1 more assumption. So from a theoretical point of view, this is maybe a bit less satisfying. And BS3 managed to achieve OM of 2, so the stronger notion, and is proven by under CDH. But it's a lot more inefficient in terms of signature and communication size. So this is roughly poly. So yeah, I think it was roughly in the 10 kilobyte range. So our work essentially tries to optimize this. And what we do give is a scheme that has still very good signature size, I would say. So 1 more group element, 1 more ZP element compared to the first 2 constructions. Communication size is still poorly, but it's, at least in terms of concrete efficiency, better than BS3. And in terms of security, we also get OM of 2, but the assumption is DDH. So this is kind of a bit worse than CDH, but I would say it's still a lot better than a 1 more assumption. Right, so this is our result, and I briefly, and in the next part, I want to give you an overview of our constructions and kind of what CTZ does, because our constructions build based on them. And I'll also try to give you at least a high-level intuition for the security proof. So CTZ essentially, at least in my point of view, the main constructive insight is that we can essentially replace pairing-based verification for a pairing-based blind signature scheme with a Fiat-Shamir compiled Sigma protocol. And then we can essentially build pairing-free blind signatures. And the first, so BS1 and BS2 is based on BLS. So I mainly talk about these 2 schemes. So essentially what BLS is, it's just a very compact blind signature from pairings. And the signature has the form X times H of M if we write the group additively, where X is the D-log of the public key and H is just a random oracle. So so in order to now build a blind issuance protocol, CTZ essentially proceeds as follows. They first essentially go through the standard blind issuance protocol of BLS. So essentially first they blind the message. This is kind of like a commitment C, then this commitment is signed, and later on the blinding factor is removed. So now we have a blind signature, but we cannot, of course, verify this without a pairing. So what they do is they add a interactively computed Fiat-Shamir protocol, and then this is blinded and compiled into a Sigma protocol, and this is then interactively computed and blinded. This is then blinded and compiled into Fiat-Shamir on the user side. And this then builds the final signature. So this then we essentially obtain a NISIC pi, which you can think of just like a Schnorr-style NISIC that proves essentially that the signature verifies, and also the signature. And this kind of builds the final blind signature of the protocol. And in order to come up with our construction, we essentially do something very similar and intuitive. So instead of basing our construction on blind PLS, or for example, BS3 in their papers also based on another pairing-based blind signature, and instead of choosing those schemes, we choose a recent scheme from KRS 23. And in this scheme, essentially, the signatures have the form that, S1, S2 that I've written here. The form is not really important. Kind of what I want to highlight, it's essentially derived from an Bonnet-Boyan IBE. So this kind of, this generic IBE to signature transformation. And I just want to highlight that the signature is also reasonably linear. So essentially, KRS built a blind issuance protocol. So we essentially use this blind issuance protocol here also. Just as a small note, they also need a proof of Patterson opening. So essentially C is essentially a Patterson commitment, and they need a straight line extractable proof here. I'm not going to go into too much detail. But yeah, this is essentially a source of inefficiency in their construction, and that's why they have poly. Other than that, yeah, essentially this is a reasonably intuitive construction in terms of blind issuance. So essentially now we have a pairing based, so this scheme can be verified using pairings. But again, we don't want pairings. So we again add a Sigma protocol in the interaction, and this is again blinded and compiled into a NISIG using Fiat-Shamir on the user side. And now we essentially end up with a blind issuance protocol in the pairing-free setting that, apart from the proof, is reasonably efficient, or actually quite efficient, I would say. So the question is, of course, can we prove security? And in terms of blindness, the answer is reasonably intuitively yes. So we can just rely essentially on techniques from KRS-23 to argue that S1 and S2 is blinded, and this commitment doesn't leak any information about the message. And in terms of the Sigma protocol part, we can essentially rely on techniques from ZTZ to argue that the proof pi in the end is essentially distributed uniformly or independently from the signing session. So this is, this is in terms of blindness. The interesting part is one more on forgeability. So in order to give you at least a high-level idea of what happens, I'll briefly recap the approach of ZTZ-24. So essentially, you cannot just instantiate the NISIG with a standard Sigma protocol that the signature is well formed, or verifies correctly, because then you cannot simulate anymore. So what they do is they prove that either the signature is well formed, or they know, the prover knows the D-log of some public key element Y, or this is essentially something just to give a simulation branch with which we then can later on simulate signing, even if we don't know the signing key for S. And then knowledge soundness essentially guarantees that the signature is of the correct format, or we can learn the D-log of Y. And then the proof strategy of ZTZ is essentially that under the D-log assumption, they argue that S has the correct form in the sense that S verifies correctly. And then they switch with which branch they sign in the Sigma protocol. And then they use the D-log of Y to simulate without knowing the secret key. So the argument is a lot more subtle than that. So it's actually quite technical. And they essentially managed to prove this, but what they need in the security proof is that the output of the signatures that are output by the signer, they must be well formed, even if the other branches is used. So even if the signature branch is simulated, the signatures that are output must still be well formed. And in terms of what this means for security is that for BS1 and BS2, they must simulate with one more CDH. So they can only argue OM of 1. And for BS3, they actually managed to prove full OM of 1 and OM of 2. OM of 2, essentially because they observed that they can commit to S instead of giving S in plain in the first round, and then they open this commitment in the second round. And this allows them to get OM of 2 at the cost of increasing the signature and communication size, essentially due to this commitment. So in our construction, I just want to give you like a few, like a very high level idea of kind of things that differ in our security proof. So essentially, if we look at our construction, then if we, especially, so the main problem was that for simulation, we need that the signatures are well formed. So in this case, this is this D part. And now if we look at this, so S times G, so D2 is essentially just a random group element. So S is sampled fresh. And S times H is uniform under the DDH assumption. So essentially what we do in the security proof is that we essentially manage to, for unfinished sessions, we essentially replace this D part with random. And then we can argue that, the adversary doesn't learn anything from unfinished sessions because the first round message from the signer is essentially distributed uniformly. And then secondly, in order to get a tighter security proof, we try to avoid rebinding, and this is essentially based on the following observations. So essentially, the reason why the previous proof from ZTZ required rewinding is that the D-log of Y, in order to kind of reduce to the D-log assumption with a Sigma protocol, we need to rewind in order to extract the D-log. So in order to prove well-formedness of S, rewinding is required. Now, if we replace this with a DDH tuple, then essentially we can make this kind of like an on and off switch. The second branch where either you can sign or using the second branch, or you can just not sign because XYZ is not a DDH tuple. So this allows us to argue that S is well formed, even if we cannot rewind, or even without rewinding. And yeah, I would say that these are kind of the two main technical insights in our security proof. So to recap, we essentially give a pairing free blind signature without the AGM. It still requires the random particle model for the Sigma protocol part. Yeah, in terms of efficiency, it's kind of lies between BIS1, BIS2, and BIS3. We have a tighter reduction. Yeah, something I didn't mention, we also extended to partial blindness, and this is like roughly based on prior techniques. So I didn't want to go into too much detail here. And yeah, this would be it. Thank you for your attention, and thanks again for accommodating online talks. And yeah, I'm happy to answer questions.
Yeah, thank you for the talk. Are there any questions?
Hello, really nice talk. Can this be extended to a thresholdized version?
Actually, we're kind of working, or essentially this is a master thesis that a student of mine is working on at the moment. So it should be, I think. Of course, we don't have the full details. This is the work in progress. But yeah, I don't see like a clear reasons why it shouldn't.
Kind of to, erase the single point of failure and stuff like that.
Sorry?
Kind of to erase the single point of failure problem and stuff like that. If you thresholdize it, it erases the single point of failure thing. So that,
Yeah.
key plus one part generate the signature. So,
Yeah. So
right.
I think so. The proof is not fully obvious, and I think you need to work a bit for it. But I don't see why you cannot. For example, Snowblind also. So this is one of the works I refer to from Kreitz, Komlomala, Tessar, and Swin 23. They also thresholdize essentially one of these pairing-free blind signatures from Asiacrypt 22. And yeah, so at least a construction should be kind of possible to write down. The security proof might be a bit more tricky because, of course, you need to now also kind of take care of the other parties and make sure that your simulation kind of doesn't interfere with the information the others hold, the other shares. But in general, I don't see like a inherent problem that makes this impossible.
Okay, thank you.
Thanks for the question.
More questions? Okay, then let's thank the speaker again.